So yeah, the main idea of the talk is to give an overview of the different polar textures that we can encounter in polarization nanostructures. So also I will talk about their origins, and I will talk at the end about their functional properties that they present and how we can tune these functional properties by thermodynamic fields like temperature or electric fields mainly. So all the work that I will present here is theoretical, and it has been supervised mainly by my PhD advisor, which is Javier Junquera. But for every piece of theoretical work that I will present, there is also an experimental corroboration, which was made in collaboration with a group of Professor Rames in Berkeley. So this proves also the validity of the methodology used to discuss all the computations. So the field of topological textures was born many years ago in ferromagnets, as you may know. So due to the interplay between the exchange correlation that tends to align neighboring spins collinearly and the Dialositsky-Morilla interaction that tends to cant neighboring spins, we can have these cool features like these helix structures that I plot here, or eventually skyrmions that were predicted many years ago. And since their origins, they raise a lot of attention due to their functional properties. One particularly famous example is the racetrack memories envisioned by Stuart Parkin, which you may be aware of. And driven by all the similarities between the ferroelectric and the ferromagnetic world, the natural question that arose at that time was whether we can encounter the same type of textures in ferroelectrics instead of ferromagnets. However, despite all the similarities, there are also many differences between the two worlds. So for instance, at that time, there were no apparently electric analog to the Dialositsky-Morilla interaction in ferroelectrics. And although now there are some candidates that predict electric Dialositsky-Morilla interaction, they are not needed to explain the topological textures that I will present today. The second discrepancy is that the polarization is strongly coupled to the lattice distortion. Therefore, if we want to count neighboring dipoles, we have to pay a high elastic cost. And the third discrepancy, and maybe the most obvious one, is that the spin is a quantized quantity that you cannot get rid of, but the polarization is not. So if you stress the system and oblige it to present a very exotic polarization texture, the system can say, okay, I depolarize, and that's all. So due to all these discrepancies, the natural thinking at that time was to believe that polar textures were not possible in ferroelectric materials. However, early theoretical works at the beginning of the century do predicted them in ferroelectric nanodisk and nanodogs. So this is lead zirconate by means of second principle simulations. And then these calculations were seconded by first principle data in lead titanite, strontium titanite superlattices. In this work, we will be studying the interface between two AbO3 perovskite oxides. So this material, despite its simple structure with just 5 atoms per unit cell, it presents a very rich phase diagram with multiple ground states. So the origin of this diversity is that instead of having one leading energetic term that drives all the physics of the system, there are many energies involved that compete and interact among them. And so that just by changing the A cation, for example, we can have different sequences of phase transitions, and we can encounter metallic, insulating, superconducting character. Or more centered in the topic of this work, we can have ferroelectric materials, like it is the case of lead titanite, which are materials that typically undergo a phase transition from a high temperature centrosymmetric phase, which is nonpolar, to a low temperature lower symmetry phase presenting 2 or more symmetry equivalent polar states that are generally coupled with the lattice distortion. So for example, pointing down or pointing up. And that are degenerated in energy and with the property that they can be switched by the effect of an external electric field, so showing these hysteresis loops. However, this is not the only possibility. So we can also have paraelectric materials, as it is the case of strontium titanite, that in its low temperature, low symmetry phase, instead of showing a polar instability, it shows the antiferrodistortive motion of the oxygen octahedra. So on top of this, we are adding one more element of complexity, which is that we are building a superface, an interface between the two materials. So when we make an interface between two materials A and B, the resulting properties that emerge due to the breaking of the symmetry and the changing of the chemical environment might be completely different to the ones presented by the individual constituents. So one particular famous example is the emergence of a high mobility two-dimensional electron gas in the interface between two insulating materials, as it is the case of lanthanum aluminate and strontium titanite, or again, more centered in the topic of this work, the emergence of topological textures when we embed superlattices of ferroelectric and dielectric materials. So in bulk, lead titanite is a uniaxial ferroelectric, which means that the polarization is mainly pointing along the Z direction, and it has a strong polarization strength coupling, so around 5% along the Z-axis. So this makes very difficult to tilt the polarization. You have to pay a high elastic energy cost. Bulk strontium titanite, on the other hand, is paraelectric, so it shows no polarization. However, when we combine both of them, as you can see, we can encounter many different topological textures where the polarization rotates continuously. So now I should discuss the origin of this. So when we have a bulk ferroelectric material, the uniform polarization is the desired state, where the polarization is pointing along one direction, so the Z direction, and it is homogeneous. However, when we do freestanding slabs, or we intercalate this ferroelectric material with paraelectric materials, we create a discontinuity in the polarization. So here, the ferroelectric material is polar and wants to polarize, but in the paraelectric material or in the void, there is no polarization, so we create a divergence of the polarization. And this divergence of the polarization obviously generates bound charges that accumulates at the interfaces. These bound charges generates a depolarizing field that tends to kill the polarization, and this energy is enormous, and the system needs to relax this energy. So what usually the system does is to break in domains. So breaking into domains achieves charge neutrality at the interfaces, and this drastically reduces the depolarizing fields on the structure and the electrostatic energy associated to this structure. So as a balance between the electrostatic energy of the depolarizing field and the gradient energy of having a domain wall, this will determine the length or the width of the domains. And therefore, a compromise between these two elements must be established. With this breaking into domains, the depolarizing fields in the center of the materials are drastically reduced. However, near the interface, there are still some remnant straight fields that can make the system further evolve to a flux closure configuration like this one, where we only have left 90-degree domains walls here that are dotted and 180-degree domains here. So if the system finds a compromise under appropriate mechanical boundary conditions between the elastic energy cost that costs to tilt the polarization and the energy of these 90-degree domain walls, the system can further evolve and show a more continuously rotating polarization. So like this, with the interplay between the electrostatic, the elastic, and gradient energies, we explain the emergence of these polar textures in ferroelectric materials. So now I will present to the first work that is the first experimental observation of ferroelectric skirmions in this material. So this can be accomplished by building the lead titanite strontium titanite superlattices on top of a strontium titanite substrate, or computationally we can do this if we mechanically restrict these superlattices to be built on top of a strontium titanite lattice, so building a mechanical constraint that imposes the lattice constant of the strontium titanite, and starting the calculation from a nano domain with a polarization completely surrounded by a negative polarization matrix. So when we relax this structure, what we get is this figure, so fingers crossed for the video. Yes, it's work. So we have an inner core where the polarization points out, and it's completely surrounded by a matrix of negative polarization. And when the system is relaxed, the polarization in between rotates continuously, forming this structure. So this block pattern that continuously translates from the up polarization to the down polarization. So here is the structure. In this column, I show the dipole structure. So the arrows represent the polarization in plane, and the colors represent the polarization out of plane. So here we can have a core of polarization pointing out, completely surrounded by a matrix of negative polarization, and in between the in-plane polarization rotates continuously to accomplish these values. So if we topologically characterize this structure, we can integrate the Pointillé density, and we can check that it is by plane, it is a skirmion. So we can define transversal cuts of this structure, and all of them present the same skirmion number. So this resembles with the skirmion tubes that are usually found in magnetic systems. And one cool thing is that in the top layers, what we have is Snell skyrmions, where we have a zero rotational and a non-zero divergence. And in the middle planes, what we have is a continuous transition from these Snell skyrmions to Bloch skyrmions. However, the polar skyrmions are now just the peak of the iceberg, and many different phases have been encountered in topological textures. So we can find now vortices, we can have merons, we can have Hophions, and we can have different geometries where the polarization is confined in the plane. And the phase diagram is more or less under control, so we know that changing the thicknesses between the ferroelectric and the dielectric layers and changing the mechanical boundary conditions, we can more or less know which is the phase that will be reproduced. And I would like to stress the importance of the mechanical boundary conditions, which now experimentally can be tuned by means of the substrate mainly. So here I represent a phase diagram where we have here the lattice constant of the different substrates. And we are passing from a more compressive strain to a more tensile strain. And this, to a large extent, determines the final phase that we will be getting. So if we are imposing a compressive strain, the out-of-plane polarization is preferred. And therefore, we will have striped domains, then skyrmions. And if we continue increasing the lattice constant, we will have a transition to meron, vortices, and finally A1, A2 geometries, which are geometries where the polarization is restricted to the plane. And OK, so now before ending, I would like to discuss a bit the functional properties that this system can present. So these systems are very interesting because they can help in the design of new nanoelectronic devices. So essentially, the three main characteristics that these systems have are the negative capacitance effect that allows the ultra-low computing, although today I will not discuss about this. The chirality, these phases are also chiral and can interact with light, and also their ultra-fast dynamical properties that could be used to ultra-dense memory storage. So the first of all that I will discuss today is the chirality. So a chirality is the mathematical property that has an object that cannot be superimposed to its mirror symmetry. So the chirality in this system is also an emergent property, as bulk, lead, and strontium titanite are materials that are not chiral. However, when we combine both of them, the topological textures that emerge do present chirality. So this is also a cool thing. And this is known since many years ago. So look at the date, so 2012, where they proved that the coupling between the in-plane components of the polarization coupled with the out-of-plane components in a way that they are chiral. So we can have essentially right-handed, left-handed, or achiral configurations, depending on how this coupling of the out-of-plane components coupled with the rotation in plane. So if we have one vortex that is rotating clockwise, and we have an out-of-plane component that is going this way, this will be right-handed. If the other way around, it will be left-handed. And if the two vortices, the one that is rotating clockwise and the one that is rotating counterclockwise, have the same axial component, then the handedness of one vortex tube will cancel out the handedness of the other vortex tube. So as I said, this is known since a long time ago. But this chirality, the drawback that it has is that it is very robust, so it cannot be easily switched. And in order to apply this chirality property to nanoelectronic devices, a key property that we need to have is to have control of this chirality. So if it is very robust, it is not very convenient. And this is the problem that we faced like 1-2 years ago, so that it was the problem of controlling this chirality. So we started from a different perspective. So we started from the achiral configuration when the handedness of the two vortex tubes cancel out. And the idea was to generate some symmetry breakings on this structure that could be controlled by means of homogeneous electric fields. And these symmetry breakings would generate chirality. So in principle, we can envision two different alternatives. So either we apply an electric field along theta and generate an equal up and down polarization domains. So this breaks one symmetry. Or we apply an electric field along x and we generate a backlink between the vortex cores, so this movement of the vortex cores. And this also generates symmetry breaking along the x direction. However, any of these two symmetries are not enough to generate a chiral structure, as we have, again, these mirror planes that link the two structures. However, if we combine both of them, what we have is finally a chiral structure. So if we combine an electric field along theta and an electric field along x, that breaks the theta and the x symmetries, and we generate a chiral structure. Essentially, what we are favoring is the handedness of one vortex tubes with respect to the other. So even though they still compensate, they not compensate fully, and we still have a remnant chirality. So the drawback is that the magnitude of this chirality is much lower than the one that I presented before, but the advantage is that it's controllable by means of external electric field. So as I said, this is controllable by means of an external electric field, particularly along x. So if we apply a positive electric field, we will generate a positive polarization in plane, and we will oblige the clockwise vortex to be down here, we can see it. And if the other way around, if the electric field is negative, the polarization would be negative, and the clockwise vortex will be up. So like this, we can generate an hysteresis loop. So here we are applying an electric field along x. In blue, we are plotting the polarization along x that follows this hysteresis, and in red, we are plotting the helicity of the structure or the chirality. So as we can see here, by changing the electric field, we can generate a different backlink between the vortex cores, and this is coupled with the helicity or the chirality, and therefore we can control the chirality of these structures by means of an external electric field. That it was the first time that this was done. And well, this is the numerical values that I get, and this is the correlation with the experiment that it's pretty much perfect. So the last thing that I would like to talk about is the ultrafast dynamics that these domains can show. So typically, these domains are discussed in a low temperature regime. However, when we heat them up, they are shown to show dynamics. So they are not strictly striped domains. They can move, and also they can present cool dynamics, as I will show to that. So we can have a low temperature phase where the domains are strictly striped domains, as they are crystalline. However, we can compute the structural factor. So essentially, when we have a perfect order, what we would expect is that the diffraction pattern will show peaks of showing the periodicity of the domains. However, if this is the molecular dynamics at a reasonable low temperature, so we can see that the domains are ordered all the time, and the instantaneous structure factor is the same as the global one, because nothing is changing essentially. However, when we heat this up, what we can see is that the domains start to show dynamics. So it is an x-oriented domain that can vertically flip to a y-oriented domain, and therefore the structural order parameter changes and resembles a transition that is similar to the ones faced in liquid crystals. So the translational order now is distorted, but the orientational order is preserved. So here I have a video where we can see that by means of temperature, the dynamics is, we started with an x-oriented domain, and now we have transit to a y-oriented domain. So this is very cool because it has a terahertz frequency, and what we can see is that we can indeed tune the frequency of this hopping by means of temperature. So here I show the difference in the frequency when we heat up. So in blue and in green are two different realizations when they are oriented along x or along y, and in red is at higher temperature where we have hoppings. And what we can do is compute the frequency rate of these hoppings as a function of temperature, and we have shown that it follows a Blöchel-Flügler dynamics, where we can see that the temperature tunes the dynamics of this, or the frequency of this hopping rate. And what we can see is that we can have a tuning from the terahertz to the gigahertz in about a 40 Kelvin window, which is quite cool in order to treat these dynamics. So just a conclusion, and I think that I am on time. Well, I have so many different, the many different polar textures that can be encountered in ferroelectric materials, as opposed to the ones that we have in ferromagnets. I have seen also that this has particle-like behavior and that we can tune by means of external electric fields or temperature. And also we have seen that some of their functional properties can be tuned by thermodynamic fields like temperature or electric fields. So these are the three words that I have mainly discussed today, but well, I think that I am done and I can take questions.